Over the course of science, individuals have attempted to comprehend how the universe began. The most well-known explanation has been something called the theory of prehistoric cosmic detonation. Many investigations and the work of thousands of researchers support this idea, providing evidence about how the universe started. However, in today's universe of science, new innovations bring novel ideas and perspectives. These ideas challenge our thought processes and what we consider undeniable truths. Neil deGrasse Tyson has become a significant figure in this influential universe of science. Now, something exciting is happening with the James Webb Space Telescope. It's noteworthy, something that could make us question the theory of the universe's origin. The James Webb Space Telescope has tracked down 750 new galaxies, which are not quite what we anticipated, leading us to re-examine what we assumed we knew. This telescope was designed to help us understand how galaxies form, so it's not surprising that it's stirring up how we interpret the universe. In the past, researchers said that the Big Bang hypothesis was the best explanation for how the universe began. According to this hypothesis, around 13.8 billion years ago, the universe appeared through a mysterious astronomical event. However, the images from the James Webb Space Telescope have tested this idea. These images show galaxies that are smaller, smoother, older, and more diverse than the theory predicted. According to the hypothesis, as the universe expands, objects should appear larger the farther away they are. Yet these galaxies do not follow that rule. The hypothesis also states that at the very start of the universe, all matter was pressed into a tiny superdense point called a singularity, which was unimaginably hot. This idea of a singularity comes from a set of physics conditions proposed by Albert Einstein called general relativity. Inside the singularity, all the matter in the universe was packed into a tiny space with incredibly high density, meaning there was an immense amount of mass and energy concentrated in a small area. In simpler terms, researchers have consistently said that the theory of the Big Bang explains how the universe began. But now, these new images from the James Webb Space Telescope are making us question that idea. The galaxies it found don't fit what the hypothesis predicted, and its explanation of the early universe may not be as solid as we once thought. In our current understanding, we believe that all the energy in the universe originated from a very hot and dense point, the singularity, which acted as the starting point for everything we see today. After this singularity, the universe began to expand and evolve over about 13.7 billion years to become what it is now. This expansion started with something called cosmic inflation, where the universe grew incredibly quickly, much faster than the speed of light. The very fabric of space itself expanded, and everything within it expanded along with it. This infinite expansion helped shape the universe, making it more uniform and creating the foundation for galaxies, stars, and other cosmic structures to form. As the universe continued to grow, it didn't expand as rapidly as during cosmic inflation, but it still kept getting larger. This ongoing expansion is known as cosmic expansion. Researchers have found evidence of this expansion by observing how light from distant galaxies shifts in color, known as redshift. Now, let's discuss those astonishing images of new galaxies taken by the James Webb Space Telescope. To most people, these photos are stunning with many galaxies in a single frame. But for researchers, it's a bit of a shock. These images don't align with what their theories predicted. First of all, these galaxies are much older than expected, which challenges our understanding of how galaxies form and evolve according to the Big Bang theory. Additionally, there are far more galaxies than we expected. The theory of the universe's origin predicted a certain number of galaxies and how they would be distributed, but the James Webb Space Telescope images reveal a much larger number than anticipated. This makes researchers question whether the theory's predictions are accurate. Some researchers are even starting to panic a bit because these discoveries don't match their expectations at all. Another surprising aspect of these new galaxies is their smoothness, which conflicts with what the Big Bang theory proposes. According to the hypothesis, galaxies should show irregularities and variations in their structures due to how they formed and developed. However, the images from the James Webb Space Telescope show galaxies that are unusually smooth, lacking the complexity and roughness we would expect. During the early universe's expansion and cooling, changes occurred in particles like protons, neutrons, and electrons, which began to interact with light and energy around them. These interactions played a crucial role in shaping the development of matter in the universe. In the initial moments after the Big Bang, a process called nucleosynthesis took place, involving the creation of light elements like hydrogen and helium. These elements set the stage for the formation of stars, galaxies, and more complex elements as cosmic history unfolded. This combination of basic building blocks was a critical step in the universe's evolution, transitioning from an early state of particles and energy to one where matter began to take form. The Big Bang theory had predicted that we would see galaxies that were messy and chaotic due to collisions. However, the James Webb Space Telescope images tell a different story. Instead of turbulent and scattered galaxies, the images reveal smooth, organized shapes similar to the galaxies we observe today. This startling finding challenges the idea that mergers are a common part of galaxy formation. If there are few or no mergers occurring in these galaxies, as suggested by the Big Bang theory, it becomes unlikely that small galaxies could grow to become much larger. Additionally, the optical illusion predicted by the expanding universe theory, where objects appear smaller as they get farther away, doesn't seem to be present. Astronomers have noticed a striking pattern where galaxies tend to cluster together in large groups, forming intricate networks across the universe. This large-scale structure aligns with the expectations of the Big Bang theory. According to the hypothesis, the universe began in a very hot and dense state, and then slowly expanded and cooled over time. As the universe expanded, gravity played a key role in shaping how matter was distributed, leading to the clustering of galaxies and the formation of interconnected filamentary structures known as the cosmic web. The presence of these galaxy groups and the cosmic web structure strongly supports the Big Bang theory. How galaxies are distributed across the universe aligns with the gravitational effects predicted by the hypothesis. These factors, including the clustering of galaxies and the cosmic web structure, provide solid evidence that the universe evolved from a dense state and has been expanding for billions of years. Now, let's return to the size of the galaxies found by the James Webb Space Telescope. These images contradict what we thought we knew about the Big Bang theory. According to the hypothesis, small galaxies should grow and expand through collisions with other galaxies. However, observations made by the James Webb Space Telescope cast doubt on this idea. If galaxies were colliding and merging as expected, we would see evidence of these interactions in dense, interacting galaxies. However, the images show something different. While the Big Bang is a theory, it is supported by undeniable evidence, including observations of the redshift of light. Evidence from distant galaxies supports the expanding universe theory. Observations showing galaxies moving away from each other in all directions suggest continuous expansion, as predicted by the hypothesis. The abundance of light elements like hydrogen and helium throughout the universe also aligns with the Big Bang theory's predictions. Furthermore, the large-scale distribution of galaxies revealed through surveys matches the patterns anticipated by the theory. One of the most significant pieces of evidence for the Big Bang theory is the discovery of the cosmic microwave background CMB, a faint radiation that fills the entire universe and represents the afterglow of the Big Bang. This cosmic radiation, first detected in 1965, closely matches the predictions made by the theory. The observed properties of the CMB, including its uniformity and temperature distribution, strongly support the idea that the universe was once in a very hot and dense state before undergoing expansion, a central component of the Big Bang theory. The discovery of the CMB is a crucial piece of evidence that offers a unique glimpse into the early moments of the universe. It acts as an echo of the initial stages following the Big Bang and has played a pivotal role in solidifying the theory of the universe's origin as our best explanation for the universe's beginnings. However, recent discoveries have challenged some aspects of the Big Bang theory. The existence of galaxies with ages that seem to predate the Big Bang contradicts the theory's main premise, suggesting that the Big Bang may not have happened as initially believed. Additionally, not everything may have started from the Big Bang. Proponents of the Big Bang theory had predicted that as the James Webb Space Telescope looked further into space and further back in time, the number of observable galaxies would decrease, eventually leading to a vast dark age. However, recent research indicates that even 200 or 300 million years after the speculative Big Bang, galaxies as large as our Milky Way were common. The James Webb Space Telescope images reveal a much greater abundance of large galaxies at redshifts greater than 10 than scientists had expected, challenging the credibility of the Big Bang theory. Moreover, the Big Bang theory is associated with 16 incorrect predictions in the current body of scientific literature, with only one accurate prediction concerning the abundance of deuterium, a type of hydrogen. Some of these inaccurate predictions include estimates of helium abundance, which are off by a factor of 2, and predictions for lithium abundance, which are off by a factor of 20. The theory also fails to explain other phenomena, such as the absence of the expected illusion where objects should appear smaller with increasing distance. These inconsistencies raise concerns about the validity of the Big Bang theory. By studying the colors of distant galaxies in the infrared part of the spectrum, astronomers can estimate the ages of the stars within these galaxies. Some of these galaxies appear to have stellar populations more than 1 billion years old, contradicting the theory's assertion that nothing should have existed before the Big Bang. Despite these significant irregularities, it is important to note that the Big Bang theory has undergone constant evolution and revision based on new evidence and observations. Scientific theories are not static but rather dynamic frameworks that adapt as new information becomes available. While the James Webb Space Telescope's findings present challenges to the Big Bang theory, they also highlight the importance of continued exploration and investigation in our understanding of the universe. The scientific community is now faced with a task to reconcile these observations with the established framework or develop new theories that can better explain these findings. Science often progresses by confronting contradictions, and these recent discoveries may lead to a deeper and more nuanced understanding of the universe's origins.